Alright, welcome back. We're going to pick up in this video talking about the reaction quotient. I'm not going to spend too much time on this because we've already discussed it in an earlier video, but just to remind you, the reaction quotient is the exact same mathematical formula as the equilibrium constant. It just doesn't have to be at equilibrium. So it could be at any point in the reaction. But in terms of the math, it is still just products raised to coefficients divided by reactants raised to coefficients. One of the useful things about the reaction quotient is if you know the equilibrium constant and you know the concentrations of everything in the mixture, you can actually work out not only if the reaction is at equilibrium, but you can actually work out which direction the reaction is going to move to reach equilibrium. So if, for example, you know both Q, which is the reaction quotient, and K, the equilibrium constant, and you find that Q is smaller than K, what that tells you is that the reaction is going to move to the right in order to reach equilibrium. You need to make more products and use reactants to get to equilibrium. If, on the other hand, it is the opposite, if you have a larger Q than K, then that means that the reaction is going to go backwards. The reverse reaction is going to happen faster than the forward reaction, so that you end up with fewer products, more reactants as you go towards equilibrium. And if the two are equal, then you are at equilibrium. And so there was no need to think of it as a reaction quotient in the first place. It was actually the equilibrium constant. So let's just look at a real quick example here before we move on. This says, consider the reaction and its equilibrium constant. So we have 81.9 is our equilibrium constant. A reaction mixture contains 0.114 atmospheres of iodine, 0.102 atmospheres of Cl2, and 0.355 atmospheres of, let's see, I guess that would be iodine monochloride, I guess would technically be the name of that. Anyway, is the reaction mixture at equilibrium? If not, in which direction will the reaction proceed? So, to determine if it is at equilibrium, we are just going to plug all of our knowns into the reaction quotient equation and see what we get. So we have just one product, and it has a concentration, or really a pressure, but we can treat it like a concentration, of 0.355 squared, since there's a 2 here. We have two different reactants. One of them is 0.114, and the other is 0.102. And so, if we do the math, let's see, 0.355 squared divided by 0.114 and 0.102 gives me 10.8. So it is not at equilibrium, because if it was at equilibrium, Q and K would be the same. So because it is not at equilibrium, we need to figure out which direction is it going to move to reach equilibrium. Since Q is smaller than K, that means the reaction is going to move to the right, which is to say it's going to move to make more products. Q needs to get bigger to become the same as K. And to get bigger, we need more of this and less of this. So that's what's going to happen. Alright, so with that lesson learned, let's talk about the other option that we have when we're looking at equilibrium questions. So in the previous video, we talked about working through an equilibrium problem where we were given an equilibrium concentration. And if you've already done the determining the equilibrium constant lab, we did this in lab. We had known initial concentrations. In the experiment, we found one of the equilibrium concentrations, and we use stoichiometry to work out the rest. So that is one possibility, where you know an equilibrium concentration, but you don't know the equilibrium constant. The other possibility is if you know the constant, so you know the reaction that's taking place, you know what its equilibrium constant is at the temperature you're running the experiment, but you only know the initial concentrations. You do not know any equilibrium concentrations. And so your task in these kinds of problems is to find those equilibrium concentrations. And that can be done. You can find it as long as you know the equilibrium constant. It can be done. And as long as you know where everything starts, obviously. So you have to know where everything starts, and you have to know the constant. And you can solve for those equilibrium concentrations. And this is a multi-step process, but it's actually not too bad once you get into it. The worst part is the algebra. And I know some of you went, well, that's always my worst part. It's okay. We'll manage. We'll manage to get through it. So the first thing that you need to do in these problems is decide which direction the reaction is going to move. 99% of the time, this is incredibly obvious. We will have some practice problems and some homework problems where it's not, but most of the time, 99% might be a little bit of hyperbole. Maybe say 85% of the time, it's incredibly obvious which direction the reaction is going to move, because 85+% of the time, you will have reactants and no products. And so there is only one direction that the reaction can move. But like I said, we will see, I will intentionally have you work through some problems where it's not actually 100% clear if the reaction is going to move forward or if the reaction is going to move backward, because you will have some reactants and some products. And so you will actually have to work out which direction the reaction is going to move. But most of the time you won't have to do that. It'll just be a few exceptions where you do. Step 2, once we know which direction the reaction is moving in, we are going to define the changes of all the materials in terms of x. So we're going to say, I don't know how this molecule is changing, specifically. I don't know what the numerical value is, but I know this molecule is changing by some amount, and I know that this other molecule is going to change by that same amount. So we're going to define everything in terms of some unknown value x. Reactants are usually going to be disappearing by some amount x, or maybe 2x, depending on the stoichiometry, and the products will be appearing by some amount x. So we're going to then plug those unknown values into an ice table, and we are going to get the equilibrium concentrations in terms of x, in terms of that unknown. And we will then solve for it, because at that point we will have an equation with just a single unknown, just that single unknown x, and we can solve that. So let's look at an example here. If that previous slide just seemed like a whole bunch of Charlie Brown teacher, hopefully it'll make a little bit more sense here if we actually work through a problem. So we have the reaction that's happening, nitrogen and oxygen reacting to form nitrogen monoxide. This is happening at 2,000 degrees. Oh man, that's hot. But at that temperature, the equilibrium constant is 0.1. And by the way, it's a very good thing that you have to get this up to 2,000 degrees C to get this reaction to move forward, because nitrogen and oxygen are what you're breathing right now. And it'd be really, really bad if they easily turned into nitrogen monoxide. Anyway, getting back to the problem here. A reaction mixture at 2,000 degrees C initially contains 0.2 molar N2 and 0.2 molar O2. Find the equilibrium concentrations of the reactants and product at this temperature. So we are given nothing but initial state and equilibrium constant. One quick note here, just like in the last video, if we're not given any information about the product, we assume we start with none of it. And that's what we're going to do here. So the first thing that we're going to do here is we're going to set up our ice table. So we're going to put in our initial values that were given. Thankfully, we were just given concentrations, so we can just plug those concentrations directly in. The next thing that it has you do is to work out which direction the reaction is going in. This is, again, one of those situations where there is only one direction it can go, because you only have reactants. The reverse reaction is impossible. So there's really no need to do this whole equation here. They do it anyway. They have 0 in the numerator, and what do you know? You have 0, which means the reaction needs to proceed to the right. So, again, most of the time you won't have to do that. So now getting back to the important stuff here. We're going to define all the changes in terms of x. So what we mean by that is we know, based on the stoichiometry, based on our balanced chemical equation, that this molecule, N2, is going to decrease. We know this because the reaction is moving to the right. We're making products, and we're using up reactants. And so we know it's going to decrease by some amount, x. We have no idea what x is, but that's okay. We don't need to know at this point. We know that O2 is going to decrease by the exact same amount. Again, that's stoichiometry. This is a 1-to-1 ratio. For every 1 N2, we use up 1 O2. In addition to that, we know that NO is going to be increasing by 2 times the amount that these are disappearing. And again, because of the stoichiometry, we have 1s in front of both of these and a 2 here. And so we're going to see 2x increase in the NO as a change here. So again, we have no idea what any of those x values are, but we do know how they're related. So even though we don't know what the actual numerical value is, we can describe all 3 of these with only a single unknown. And that's really important. If we said, you know, N2 is decreasing by x, and O2 is decreasing by y, and NO is increasing by z, it's impossible to solve that equation. You can't solve for 3 unknowns with a single equation. Now, if we had 3 equations, then we could, but that would be a ton of algebra, and I don't want to do that. If we only have a single equation, we can only solve for a single unknown. And so because we are able to put all 3 of these unknowns in terms of just a single value, in terms of just x, that allows us to solve it. So if we take the change and we apply it to the initial state, which is what we're going to do every single time, no matter what kind of equilibrium problem we're doing, we're just going to apply the change to the initial state. At equilibrium, we will have 0.2 minus x of the N2, 0.2 minus x of the O2, and 2x NO. We still have no idea what x is, but this is 100% true. Those are the equilibrium concentrations. We just don't know what the numerical value is yet. So, if we take these and we plug them into the quadratic equation, what we see is it's not going to end up being quite as messy as it could be, mainly because the concentration of the NO is squared, and these two, the 0.2 minus x, are the same. We have 2 of those, and so this essentially ends up being squared as well. So the fact that both of these end up being squared simplifies the math immensely, which is really nice for us. So because both of these are squared, we can just take the square root of both sides of this equation. Remember here the 0.1, that was just from the beginning of the problem. It was given to us. That's the value of k for this reaction. So we just take the square root of both sides. That gets rid of the squares here, and so we just have the square root of 0.1 on the left. So now we're going to do a little bit of algebra here. We're going to multiply both sides by 0.2 minus x, so that gets this over here. If we go ahead and distribute that square root of 0.1 into the parentheses there, We have square root of 0.1 times 0.2 minus the square root of 0.1x is equal to 2x. Move all the x's to one side, which is what we do there. So we have the 2x plus the square root of 0.1x, which is 2.3x. And that is equal to 0.063, which is what this was, the square root of 0.1 times 0.2. And so then if we go ahead and solve for x there, x is 0.027. So then this value, we're not done yet. We do know what x is now. We're going to plug that back into here. Because again, we're trying to find those equilibrium concentrations, and we know x now. So we plug that value for x in there, there, and there. And that's what we have here. So 0.2 minus x, 0.2 minus x, and 2x. And those are our equilibrium concentrations. So then the last step that they put in here is just essentially double checking your work. So taking those numbers, plug them back into the Kc equation and make sure you get the correct answer, the true K value. All right, and so there's another practice problem if you want to get a little bit of practice on that, but I don't think I have the answer shown there. So that was a lot of work for just a single problem there, but it does become a little bit easier as you get some practice with it. And if you know how to use the solver function on your TI calculator, on your graphing calculator, even if you have to use the quadratic formula so you don't have this nice algebra setup here where the squares just go away, even if you don't have that, the calculator can solve the quadratic equation pretty easily. It's a lot faster than doing it by hand. But if you are comfortable doing it by hand, more power to you. Go for it. I'm going to let my calculator do the heavy work, though. Call me lazy. Alright, I think we'll call it there for this video. And in the next video, we're going to talk about a simplification that will make our lives a whole lot easier some of the time when we're allowed to use it. So I'll see you in the next video.